Previously, we showed that we could describe the partition function in a continuous form by using the Hamiltonian sort of equation. And so based on this idea, we could extend it to also say that we could calculate the probability that the system is in the empty state using this form here, right, where we have our Boltzmann factor, which now has the Hamiltonian instead of the discrete energy. And then in the bottom, for the partition function there, we also have the integral of the Hamiltonian. Okay. Now, just like in the previous video, we could split up this Hamiltonian into the kinetic energy and potential energy contributions. So we could rewrite the probability like this. Equal to exponential of negative kappa here, because this just accounts for momentum, divided by the integral negative kappa pm kbt. And then we have the potential term, kbt, divided by the integral of the potential kbt. Okay. All right, so we split this up in terms of the momentum and the potential. And in fact, for the probability, we could say that the probability that we're in, that's a function of the momentum and the position, we could actually define it such that we say that that probability is just a function of the probability of the momentum multiplied by the probability in terms of the position. Okay? All right, and so, this sort of definition is useful because it allows us to then, by evaluating each of these probabilities independently, that's how we get the overall probability. A couple of definitions that are key. If we take the integral of P of Pm and Rm, if we integrate that, we should get 1, right? And so that's useful in case we need to normalize or identify the partition function of our system. And some other things, some other properties that are useful that depend on position. So the average position of a molecule in the system would just be the integral of the probability multiplied by x drn, and then the variance of the position would just be the second moment of x minus x average squared.